Okay, so one more time. It's Thursday the 12th. We're going to be looking at designing our reaction rate lab, and we're also going to take a few notes to start with. So if you grab out your notes, let me see if I can get that back up for you really quick. Okay, go. All right. Today, basically, we're going to identify how factors affect reaction rate and how that relates to concentration versus time in a graph. We've got several Utah core that we're going to be going over. We already did the demonstration with dry ice, and I'm talking without the mic on. Okay, you probably have noticed already that this does not give you word for word what I'm saying. Sometimes it is sort of funny, but it gives you some of it. So going forward, whoa, let's see if we can remember how to do this. So those of you that haven't been here before, grab this out. This is your quiz, or not your quiz, your notes. We're going back over what this is. So if we look at the first one, we'll walk it through, and then I would like you to try it, and then I'll put up the answers. So the first one, P, from the periodic table, is phosphorus. So our element is phosphorus. The number of protons, all we have to do is look at what number P, or what number P is, which is 15, which is the bottom number. The bottom number tells us the number of protons, so we put that here. The number of electrons are the same if there's no charge. But if there's a charge, we look at the charge and say if it's negative, there's more protons or more electrons. If it's positive, there's more protons. Well, here we have more electrons by 3. So we're going to add 3 to 15 to get 18 electrons. The number of neutrons, it's already set up here for subtraction. So we just do 32 minus 15, and that will give us the number of neutrons. Do you have this in your notes, yes or no? No. Okay, so let's do this next one together. Na is what? Sodium, good. How many protons would it have? 11. How many electrons would it have? 10, good, because it has one less if it's positive. The number of neutrons? 12, good. 23 minus 11. Li is? Good. How many protons?
3.
How many electrons? 2, one less, good. And how many neutrons?
4.
7 minus 3 is 4. Te? It is tellurium, good. And how many protons?
52.
52. How many electrons?
54.
Yeah, 52 plus 2 more is 54. And how many neutrons?
I don't know, whatever that is.
So 8 minus 2 is 6. 12 minus 5 is 7. So we got 76. All right, how about PT? See how good you guys are. It's around gold.
Platinum.
It is platinum. Okay, how many electrons? Or sorry, how many protons?
78.
78. How many protons or electrons?
81.
81. So 78 plus 3. And how many neutrons? 123. 123. Okay, I'm going to take you up on that. Let's see. We did pretty good. Okay, so you still got to keep this in. This is going to count into our next unit. That's why I'm trying to review it for you. Keep you on top of things. All right, so with reaction rates, we did this last time where we did the water back and forth and back and forth and back and forth. And the rate of one side going down was the rate of the other side going up, right? That's basically what this is saying. Fancy words. Anytime you see a triangle, it just means change. So my change in concentration of A depends on how long I let you do it, right? So how much time I let you do it. So it depends on how much the bucket filled or emptied by how much time I let you do it and what volume of beaker you were moving the water with, right? Back and forth. So that's where we come in with the 4 and the 3 times. So if I have 3 times the amount of water that I'm moving, I'm going to get more on one side than the other side. So the rate of increase and the rate of decrease is dependent on that. So this would represent my reactants. This would represent my products. So over here I have 1A that's moving back and forth. I have 4B in the same time that I'm moving towards the product. While on the product side I only have 3C that are moving back. Okay? And each of those are different size beakers. Think of them as different size beakers. So, change in reactants or products over time. Our reactants will be decreasing, our products will be increasing. All right, so here are some things that affect reaction rate. We need to know a little bit about each of them. We're going to go into each of them on the following slide. So first of all is the nature of reactants. If I put two things together, are they going to react? If they're never going to react, doesn't matter. If they're going to react, then how fast are they going to react? What concentration? Well, if I put somebody in a school this size and say, somewhat how they'll find each other. They'll find a match. You probably have a pretty good luck maybe finding a match because you've got about 2,000 students to cut it in half because you're looking at the other side. But if I go to Lima, Montana, graduating class 3, my chances are not so great. I'll find the one. Okay, surface area, we talked about that. If I try and make Kool-Aid with chunks of solid sugar compared to powdered sugar, it's going to be a lot faster with powdered sugar than it is a chunk of sugar. Okay, pressure. This is affecting with gases. So gases will be affected by if I'm putting pressure on or not. Temperature. Some things dissolve a lot faster with higher temperatures. There's a few things that don't. And then the presence of a catalyst. This is like a matchmaker, getting them together. So, how to speed up and get a date. Let's see if we can get this started. Maybe.
Tonight.
Can we pray for the most special person in my life tonight?
Everyone has something to believe in.
She is the love of my life.
Son, I'm proud of you.
I Still Believe, based on the inspiring true story. Rated PG.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
I did just close that down, right? Hopefully it won't come back. All right, so going back over this really quickly. Whoops, here we go. Temperature is one of the things that he talked about. As I increase the temperature, the reaction rate increases. Particle size, if I make it smaller, the particle size, the reaction increases. So if I have something that is whole and I break it up and I break it up some more, the reaction rate should increase and keep increasing. Concentration, as I increase the concentration, I increase the chance that reactions are going to take place. Just like the example I gave about Lima, Montana, graduating class of 3 versus our graduating class of about 600, 700. Catalyst, remember our activation curve? It lowers the activation energy, the amount of energy that I have to put in. All I have to do is tell the matchmaker what I want, basically, and they go out and look for them. Okay, so that is lowering the activation energy, making it smaller. It can look really weird like this, or it can be just a smooth curve underneath. We did the dry ice demonstration. What did we learn last time? It was cool, right? It was really cold. Okay, what did we learn about it though? What was the difference when I put it in the hot versus the cold? Right, it went straight up, right? Rather than just sort of falling over. It had a lot more energy, so the gas came out and it was straight up. And it finished sooner. If you noticed, it didn't hang around. Whereas the cold, it did hang around a long time. And in my cold, that was a big chunk, it actually formed ice around it and stopped it from reacting very much at all. And I had to turn the heat up to finally get that ice to melt so it would react. All right, so we're going to be able to, over time, graph a concentration and look at what's happening here. This would be a reactant, and over time, I'm losing my reactant and finally going away. This one hits 0. That means that reaction's probably not going to go the other way. Bromine here is decreasing and is being used up. If I have a steep slope here, that means the reaction's going faster. If I have a more gradual slope towards the end, I only have a few bromines left in the solution, so it's harder for it to be found and get the right energy and the right orientation. So down here at the end, the reaction's slower. So we've got to, when it's a more gradual slope, it's a slower reaction. When it's a steep slope, faster reaction. So this is sort of what we're looking at here. We're looking at the slower reaction. When the reaction is flat, or when the slope is flat, that means the reaction's over, or that I've come to an equilibrium like we talked about last time. So when I hit a flat slope, my reaction has hit equilibrium. In order to find the rate, it is rise over run, which is your slope. And you can find at any point along the graph. It is not stagnant. The rate is not fast all the time, or 12 meters per second or molar per second. It's not that all the time. It's continually changing. Okay. There's a PhET simulation that we're going to go back and do in a little bit. I want you to play with it and see what makes the reaction faster and slower, but we're going to go on and talk about this one more time before we do, and then we're going to do the presentations that I keep forgetting to have you do about your water and air, because there's only one that did it, and we need to get the rest of you in there so you don't have zeros there. All right, so basically we did the pre-lab write-up on the factors. We hopefully last time decided what one you were going to test for what, concentration, particle size, and temperature. We didn't have a lot of time to write up. The first reaction was sulfuric acid with sodium sulfite. Remember that you're going to put a reference on the lid and a reference inside of your universal indicator, so you know when the gas is there and has been produced, so it changes color. On the other side, you're going to decide drops. Remember that I told you 5 or 6 drops is the maximum you want to do. Maybe 5 is what you want to do, because you can do 1 and 4, you can do 3 and 2, you can do 3 and 2, you can do 4 and 1 of the different ones. And you only need to do 3 experiments, but you could do all of them. Okay, they don't take that long, but you need a minimum of 3. Okay, the more the better, because then you can see the trend. The next experiment that I did was with the well plates, and I did 1 well. And again, you're going to need to do at least 3 trials here. Oh, let me go back here. This one we could put on a plate where we put ice on the bottom, or put hot water on the bottom, or just did it at room temperature, or did it at a varying temperature in between. We could also change the varying drops, so the concentration. This one was not good for particle size, remember, because there's no particles to cut up. The next one right here, we're given magnesium ribbon, hydrochloric acid, and you'll have some distilled water that you have available. I told you probably want to do at least 20 to 40 drops total. You never want to go under half of it being hydrochloric acid and half water, because it'll be too dilute to react. And then you'll be sitting there with magnesium ribbon that never reacts. You'll be given a piece of magnesium ribbon. You can cut it into however many pieces you want to do however many trials you want to do. But you have to use the same amount of ribbon every time. Now you can cut the ribbon into different sizes. So I could do one, I could cut that into a 1/4 and use a 1/4 that's whole. I could use a 1/4 that I cut in to half, making it 8ths, 2/8 put in. I could cut it into smaller parts, maybe 3 pieces, and then I could cut as many pieces as I can and put it in. Or I can change the concentration of the hydrochloric acid versus water in a total. So I could say I was using 30 drops. I could use 30 drops and no water. I could use 25 drops and 5 drops of water, 20 drops and 10 drops of water, 15 and 15. So however you want to do that, that will work. You could also put the plate on ice or on hot water or just plate. Okay, but remember 3 trials is the minimum. The last one we're going to be doing outside, it's going to be the Alka-Seltzer and the film canister, and this is the reaction for it. You can remember I told you you're not going to change the concentration on this one. You're going to be between a 1/4 and a 1/2 as far as what you're going to put in here. I told you somewhere between there is what you want to use. So you can use hot water, cold water, warm water. You're going to get 1 tablet. You're going to break it into 4 pieces, so you can do 4 trials. Remember I told you this one, we usually have at least 1 trial that fails, so you want to make sure you set up for at least 4 trials. You might end up coming back and say, Mrs. Howell, I need some more, because we had 3 trials that failed. But you're going to take and say, I decided to change the particle size on this one because this one's the easy one to do particle size. I'm going to put 1 in with, say, 1/4 of a thing of water. I'm going to turn it upside down on the lid, and the reason why I have you do it upside down on the lid is the canister is a lot easier to find outside than the lid is. And if you have the canister fly rather than the lid, it's easier to find. And it's easier to count how many bricks high, because remember on this one we're doing time and how many bricks high, so you're going to have 2 graphs. And then the next one, maybe I hand crush it in half, and the next one I hand crush it as hard as many pieces as I can get, and the next one I use a mortar and pestle and get it powdered. So there's lots of things that you can do. You choose which one you're going to do. Again, minimum of 3 tests. You have this that we started filling out for one of them last time. Remember, you've got to have a balanced equation. The only one I didn't give you the balanced equation is the one that we did last time. So the others you just pull from the front. The problem is just changing this top sentence into how does concentration affect reaction rate? How does temperature affect reaction rate? How does, what was the other thing we're doing? Temperature, particle size, particle size affect concentration. And then your guess, hypothesis, IV. Who can tell me what IV was? Independent variable, and that's the thing you're changing. Dependent variable, for the most part, is going to be just what? Time. The Alka-Seltzer one's going to also have number of bricks high. Constants, anything else you're holding constant. So think of everything else you're holding constant. The procedure, you're going to write up what you do and tell me how you're doing it. Now make sure that you do it well enough that somebody else could grab your write-up and be able to follow it in lab and not try and guess, well, I think they meant this here, I think they made that. And then you need to have a data table of what you're going to grab. So for sure you're going to want time, and maybe you're going to want to tell, like, how am I varying the concentration or the particle size. You're going to have trial numbers in the first column. This is going to be your time or your number of bricks. So when you do the one that's the Alka-Seltzer, you're going to cut this graph in half so you can have one that's time and one that's number of bricks. On the bottom is your trial number. Okay? Then you have error analysis. So if something went wrong, write it down. This happened. I put one too many drops. Or like I had the last time where I had the indicator on the top and it sort of slid and it was sort of hard to see. Maybe I put that down. Then in conclusion, you make sure you have your CER. My claim is temperature does this. Temperature affects the reaction rate this way. What's my proof? My graph, my table, something, you know, show me, and then pull it together because of my reaction rates or my time over the 3 things, then. So it's an if-then statement, sort of. Okay, so make sure you're careful here and make sure you write the right one on the right one. That seems to be the biggest problem, is they'll write particle size on concentration or they'll do temperature on concentration. So make sure you're writing the right one on there. Okay, and then that's where we're at. So we're going to do our presentations real quick, and right after our presentations, we'll go right into writing the reaction rate lab stuff. Okay? Who has their presentations ready?